right, ladies and gentlemen, so today we're going to be taking that discussion that we had in class with our technology activity using our calculators, and now we're going to get some more formal definitions. So what we looked at and what we're going to be focusing on now are these things called exponential functions. So an exponential function is a function where the exponent is the variable. This is the general form for them, right? A is a coefficient, and B is your base. And depending on how you change those, you're going to have different types of graphs, which is what we took a look at in our activity yesterday. So exponential growth function is a function where B, your base, is greater than 1. You're not going to have any x-intercept. It's not going to hit the x-axis. Exponential decay is where B is between 0 and 1. In other words, it's going to be shown as a fraction or a decimal. And you should hopefully have seen what those look like. So down in here are your key words, and hopefully you'll see if we kind of go over these. So in an exponential growth, your function is increasing, right? It's increasing from left to right. It's also, if you talk about our domain, which are our x values, you're going to have all real numbers are your x values, but your range, your y values, are going to be greater than 0. You're not going to have anything down here in this area of the graph. In a decay is decreasing, right? When things decay, they lessen. That's what that's talking about. So again, our range is all reals our domain is all reals. Our range is all positives, greater than or equal to 0. No x-intercept, no y-intercept. So you can go through and kind of read those. So let's take a look at what's happening here. So in my graph, y equals 3x, just to help you understand what's happening. My a would be 1, that's the coefficient. My b would be 3. So just so that you can see how those relate to each other. So we're going to pick some values for x, put them in, and figure out what we're going to get. So I'm going to do -2, -1, 0, 1, and 2. All right, those again, even when we were doing linear equations, those are kind of your standard ones that you pick. So this means 3 to the -2 power. Well, we just talked about what negative exponents mean. That means this is really 1/9. Then I have 3 to the -1st power. Well, that means 1/3. 3 to the 0 power, we know anything to the 0 power is 1. 3 to the 1st is 3. 3 to the 2nd is 9. So now when I try to graph those, so I have -2, and we're barely above the x-axis. For -1, 1/3, we're a little bit more above, but still not much. Then all of a sudden we're going to jump to 1, and then at 1 we're going to jump to 3, and at 2 we jump to 9. Let's see, 3, 4, 5, 6, 7, 8, all the way up here at the top. All right, so again, like we saw with our graphing calculator activity, these form curves, right? And then they kind of flatten out as you come to the x-axis. So it says state the domain and range. So your domain are all reals. Your range, y has to be greater than 0. Right? So your y values, only things that are greater than 0, because you're not going to even hit that 0. That's why I didn't put or equal to. All right, let's try the next one here. So this time we're going to graph y equals 1/2 x minus 1. So now they've even thrown in something else. Find the y-intercept and state the domain and range. Oh, I forgot the y-intercept. Sorry. I think they asked for that back here. So the y-intercept is when x is 0, so your y-intercept is 0, 1. That would be the point for it. Sorry, back to here. So this time, because I have half, I'm not even going to change this because it's my exponent. So I'm still going to do -2, -1, 0, 1, 2. So this tells me that this is really 1/2 to the -2 minus 1. Well, this means when I have a negative exponent, it's really doing the reciprocal. So this is going to become, I'm going to just put it up here, 4 minus 1, which is 3. Here I'm going to have 1/2 to the -1 minus 1. Do the reciprocal, that turns it into positive, so this is 2 minus 1, which is 1. 0, we know anything to the 0 power is 1. 1 minus 1 is 0. Then we have, 1/2 to the first minus 1 is negative 1/2. And then 1/2 to the second minus 1 is negative 3/4. So negative 2, 3. Negative 2, 1, 2, 3. Negative 1, 1. 0, 0. 1, negative 1/2. 1, negative 1/2. And 2, negative 3/4. Looks like this. So this time, because we had this minus 1 in here, that now gave us an x-intercept. But that's because it had the minus 1 going on. So the function, C equals 179 times models the amount of soda consumed in the world, where C is the amount consumed and T is the number of years since 2000. So 2000 kind of counts at 0. Graph the function. What values of C and T are meaningful in the context of this problem? Use your calculator. So if you put that into your calculator, and you have to kind of make sure you're being careful of how you enter that. So we're going to have 179 times 1.029. Now, you can still put just the x, raise it to the x power, since we're dealing with our x and y graph. So you don't have to enter it as a t. So when you graph that, let me just kind of give you a sketch here. I have to tell you, my calculator's being a little bit slow. I'm not getting a graph. Why not? Oh, probably because my window's all messed up. Hold on. All right, I apologize. I'm not able to get a graph for this right now, so you guys sketch your graph, see what it gives you. I need to kind of figure that out. But what values of C and T are meaningful for this context? Well, if I'm starting at 2000, if that's my baseline of 0, that's really kind of year 0, then I'm not going to have any negative exponents. So T has to be positive. T has to be greater than or equal to 0. Okay, so that part's going to happen. And so the value, so even if I put in 0 as my lowest one, so C has to be at least greater than or equal to 179. All right, so that is probably what's happening with my window here, but that's okay. So how much soda was consumed in 2005? Well, there's been 5 years since 2000, so my T is 5. So this is now a calculator activity. So 179 times 1.029 to the 5th power. And that you can just plug in normally. 179 times 1.029 to the 5th power. And you're going to get 206.5, and what was this? Billions of liters. That's a lot of soda. Okay. Number 2, determine whether the set of data shown below displays exponential behavior. Write yes or no, explain why or why not. So the one thing that we can look up is, first of all, if it's a linear, that means there's a constant rate of change. So when I look at this, I'm going down by 32, going down by 16, I'm going down by 8, down by 4, down by 2. So right away, this is not linear, because here I'm going up by 5s. So does this show exponential behavior? Yes. And if I look, my y values are getting cut in half each time, and that's a definition of an exponential graph. So the y values are being halved. All right, it's not a constant adding or subtracting, they're actually being half of each other for every 5 years. Determine whether the set of data shown below displays exponential behavior, right? Yes or no. So again, I'm first going to look to see, well, is it linear? Because that's kind of the easiest way to check. So here I'm going up by 4s each time. Here I'm going up by 3s. I know I'm doing it backwards. Well, because this is constant, that is not exponential behavior. So this would be a no. It shows a constant rate of change, which means if I were to have graphed that one, that would give me a linear function. All right, I think that's it. Yep. So again, we're kind of looking at, and we'll take some time to go over and do a little bit more with these in class, but you're going to be getting these nice curves, right? It means something's increasing or decreasing at a faster rate than linear, so it's not constant. Any questions? Bring them to class.